exactly like a structure in C, if you're familiar with that. It's a bit like a class in Python. Yeah, it exists in lots of programming languages. On the screen, I've got 3 examples of structures. So you might, for instance, have a playing card, and you would use the structure keyword to say you're going to declare a structure. You then give the name. You then say where, and then you give a list of fields that are indented. And so each field is the name, followed by colon, followed by the type. So here, the card, for instance, has a suit, which is, I'm going to give it a number between 0 and 3, because we haven't done inductive types, and it's just easier to number them. So clubs are 0, spades are 3, or whatever. And the value is a number between 0 and 13, not including 13. Probably more representative example is a point. So just a point in 3D space, you've got the x and the y and the z coordinates, each of which is a real number. And you can put structures inside other structures. So here I've got a line segment with a source and a destination. It's important to note this is a directed line segment, because if you were to swap the order of the points around, Lean would consider it a different object. Once you've defined these structures, you actually need to be able to create a value of that type. And so Lean has way too many different ways of doing this. So these all construct exactly the same point. The first one is in some way the prettiest, and you say def point, but instead of putting the colon equals at the end of your def, you replace that colon equals with a where, and then just like when you define the structure, you can indent all the fields and declare them one by one. For things like a point where you don't really need the names, you just know there are 3 coordinates and x always comes first, you can use this angle bracket notation, which you can ask VS Code how to type it. So here we're still putting 2 as the x, -1 as the y, and 4 as the z, and that's the anonymous constructor. There are 2 more spellings that are interesting. This curly bracket spelling is like the where one. It lets you name all the fields, but because it appears after the colon equals, you can use it in more places, which we'll see in a second. And then the last thing is that all of these are really just notation for this point.mk function. And point.make is the constructor for point objects. And so that's actually what's going on when you write any of these other things.
MK is some fixed built-in thing.
MK is the default name of the constructor for anything you use with the structure keyword. There is one example right at the very end of this presentation where you call it something else, but it's very rare to need to do that. And there's a really important trick for when defining structures in VS Code, and that is if you write what I've written on the bottom of the slide with an underscore, and you put your cursor on that underscore, you'll get a light bulb that pops up. And when you click that light bulb, it will generate this version of the structure. So you don't need to know what the fields are of the structure. You just click the light bulb, and it will tell you what all the fields were that you expected to define. There is a keyboard shortcut for that. I think it's Alt-Shift-Dot, but it depends on what operating system you're on. Slightly more complex example, here's how you construct a term of a nested structure. So we can use where for the outermost level, but the where syntax, for whatever reason, isn't valid inside that. So now we switch to the curly bracket syntax to define this inner source. And so here we've defined a directed line segment from the point 012 to the point 345. And again, you can use this anonymous constructor notation with the angle brackets to do this all in one dense, unreadable line. Structures can't just contain singular values, you can also put functions inside them. So the first thing here is a sequence of real numbers indexed by natural numbers. You can have sort of a tuple of n real numbers where n is itself part of the tuple. So this is in some sense a sigma type. So I'll get back to that one in a sec. And the last thing is you might have a relation inside a structure, which is just a function that takes 2 natural numbers and returns a proposition. So to give examples of these, you could define the sequence of the squares, which is just every term is a function that takes the index and produces that index squared. Or you could define a relation between natural numbers, where the relation is a function that takes m and n, and it says either m is n plus 1 or n plus 1 is n, so they're adjacent values. And Lean has special syntax for this too. So if you have a where and one of your fields is a function, you can instead move the variable name from after the word fun to before the colon. And these mean exactly the same thing. This is just a nicety. There's one more slightly more advanced thing you can do, which is you can pattern match as part of the definition. So here we've completely removed the colon equals at all. And so here we've said we have this relation where the pair 0 relates to 2, 1 relates to 1, and 2 relates to 0. And for everything else, the relation is false. And so this is just demonstrating all the different things you might see inside a where clause, and it's really quite large, and maybe you just want to stick to the simple ones when you can. This bundled tuple case, we saw this notation at the end of the previous talk, this exclamation mark. So exclamation mark square bracket 123 is creating a term of type fin3 to the real numbers. And so we've specified in there just to say there are 3 elements. But generally, the point of the slide is that you can put all sorts of things inside a structure. They don't just need to be values. And there is special notation for functions. Once you've defined these structures and you've defined some constants of the structures, you might want to write a function that consumes two structures and produces another structure. And the way you do this is with dot notation. So here we're defining a function that takes in 2 points, or maybe thinking of them as vectors makes more sense. And it sets x to be the x part of the a point plus the x part of the b point. But instead of writing out this long-winded point.xa, you can use a.x instead, which is exactly the same thing. And we could use the angle bracket notation here as well. So there's always an angle bracket option for writing things quickly. There's one more way to build things with structures, and that is to use the notation that you would have seen with R cases. So here we're doing a pattern match against a point. And what we're saying is we're going to match the first point, which we know has an x, y, and a z component. And we're going to match the second point, which we know has an x, y, and z component. And now when we implement the function return value, we don't need to mention a or b at all. We directly have those components available. And these are all the same thing. This addition function we wrote, we would normally put it inside a namespace that has the same name as the type we're working with. So here, the type is called point. So we put this add function inside the point namespace. And we can either do that by just putting it between the word namespace and end, or we can directly just call it def point add in the definition. And the reason we're doing this is that if it's in the namespace, then when you write p1.add p2, that is translated to point add p1, p2. So it reduces the length of the names without you having to call your function add, which someone else might have wanted to call add. And generally, not just the functions, but the theorems too, everything about point you would normally put in that point namespace just to keep it out of the way of other people who want to name their lemmas about their other objects that happen to coincide. Structures can take arguments. So we showed a definition of a point that it was the constant point at the origin, for instance. And we can do the same thing where we have a point, but it's not just a point over the real numbers, it's a point over some arbitrary type. So instead of having x is a real, y is a real, z is a real, we take r to be anything, and then we instantiate all the variables in terms of that. So for instance, we can define a point that's a real number using this class. Sorry, not class, I did not say class. We can define a point using over the real numbers with this structure, or a point over the integers with the structure, and we've only had to write the structure once. So these are sort of like template arguments in C++, if that means anything to you, or yeah, this is dependent types is another way of looking at it. Was there anything else in that? No. So we saw we can write this dot add notation. So we at least get to write the word add between P1 and P2, but that's still not very mathematical. We want to be able to write a plus symbol. And the way we do that is we use this add type class. I'll explain what type classes are for a moment, but for now, the key thing is to know that you can write instance : add, the type you want the plus operator on, and then you write what the addition is defined in terms of. I could have written point add inside these curly brackets, or instead of here, but I'm sort of showing you would write this instead of ever writing the add function in the first place. You would go directly to writing this notation. And then we can, just to test this, we can write the example of adding the point that is the unit x direction to the point that is the unit y direction, and Lean is happy to know that, yes, that plus exists, and it will compile it for us. The exercises will have you also define 0, scalar multiplication, so like scaling each part by a real number, negation, and subtraction, or I can't remember which of these are actually in the exercises, but most of them are. Yeah.
Okay, the next slide was answering.
Okay. Yeah, so what does this instance keyword mean? Instance really is just generating a definition for you, and all it's doing is it's making up a weird name for it, and it's tagging it with this instance attribute. Which doesn't answer all the questions yet, but like the syntax has been demystified. Now the question is, what's that instance attribute doing? And what's add? Add is like a parameterized structure. So it has a single field called add that takes 2 elements of a type alpha and produces another alpha. But instead of using the structure keyword, we use the class keyword. And the question is, what's the difference between this and using the structure keyword? And what you can do is you can ask Lean, what is this? Show me the information about this add.add field we just created in both cases. And on the instance, it's got these square brackets around the self argument. And on the structure, it has the round brackets. And so what this means is if you're using the ones with the round brackets, you can't use add.add unless you tell it, unless you explicitly pass inst add point. But if you use the one without the prime, with the square brackets, then Lean will fill that argument automatically for you. So it will go over everything tagged with instance, and it will see which ones could fill that argument based on the other information it has. Classes are like a bit like traits in Rust, or they are type classes in Haskell. So what exactly is going on here? So when it's auto-filling this instance, so x plus y, we're going to pretend it's notation for add.add x.y, which is almost true and was very true in Lean 3. When you write add.add xy, add actually has these two implicit arguments you can't see. So really, it's like you wrote @add. You told it you're adding points. You didn't tell it how it was adding them, and then you told it you're adding x and y. So Lean has to fill in this underscore, and it knows it has type add point, so it looks through all the instances that might have this type. And you can use the synth instruction to see exactly what it finds when it does this. And there's some extra logging you can turn on, which is in the exercises, and it will give you this long trace. Here it's quite short, but it can be way, way longer. And so what you can see here is these are all the ways that Lean knows at this point in the exercise file how to find an add. So it knows if you've got an add 0 class, which you might see in the next lecture, you might not, an add semigroup, some weird distrib thing, and that last entry is the one we just defined, the inst add point. Lean gets it right first time and just tries inst add point. I don't know if that's because it is cleverly matching or if it just tries from the end first, but either way, if you don't know why it's finding an instance or you want to know if Lean can find your instance, synth is the command to use. So how do you pick between class or structure? A good question is there a canonical value for this definition you're creating? So I'll actually start with the structure. If you have, there's no canonical point, right? You can maybe claim the origin is somewhat canonical, but it's not so canonical that no one would ever dream of using a different point. Whereas for addition, on the real numbers, you'd be very hard pushed to find someone who disagrees what a plus sign means on the real numbers unless they've written a paragraph saying we're going to do something weird with the addition sign for the next section of this paper. And similarly, if you want to show that a type is finite, there's only one way to provide a set of elements in the type, because any set you provide must contain everything in it, so it doesn't really matter how you implement it. It's canonically the set of all the elements. If Lean's fin type were not implemented as a set, but it were implemented as a list, it would then be a bad type class because there's no canonical order for some objects, or at least you'd have to agree a canonical order. So it's all about canonicity. Some more examples, which I won't explain in this lecture, but you will see them in the next one. If you have a type M, usually there's an agreement on what the monoid structure on that type is. So on the natural numbers, the monoid structure is multiplication because monoid refers to the asterisk symbol. On the reals, it's the same thing. There are some areas which are a bit gray, and usually it's just consensus of the community. But for things like submonoid, if you have some monoid M, there is no canonical submonoid of that monoid, because obviously there's the top submonoid, there's the bottom submonoid, there's probably some in between. None of those are canonical, and so therefore submonoid should not be a type class. And same for monoid hom, which is the type of morphism from one monoid to another. There's no canonical monoid hom. Maybe you can say the identity is canonical, but that only works when the two monoids are the same. Okay, so far, all we've looked at are structures that contain data. We haven't looked at any structures that contain proofs. That's what we're going to look at now. But before we look at structures that contain proofs, we'll look at how to prove things about structures. One of the first things you want to prove about structures is what your definitions do. So we define addition, but we hadn't yet told Lean how our definition is defined. So here we say, given we've defined our definition, we're now going to tell you that when you take the x coordinate of the addition, that's the same as adding the x coordinates of the pieces. And this is true by definition, so we just prove it with the REFL term. But if we didn't do this, then the simplifier wouldn't know what to do. So it's important that we prove this, we tag this with simp, so the simplifier is trained. But it's also important we prove it by REFL if we can, because then that means that dsimp can use this lemma too. And dsimp can sometimes be faster, and it generally is a good thing to try before simp if things are slow. And so because we've done this, we can now write this expression and say we're going to add 2 points, we're going to take the x component, and dsimp turns this messy expression into 1 + 10 = 11, which we can then solve with norm num. Possibly a more interesting case of proving things with structures is when you want to prove 2 structures are equal. So an obvious way to prove that 2 points are equal is to prove that all their coordinates are equal. This isn't immediately obvious to Lean, though. And so to do this, what you need is the cases tactic. So where we saw that cases can split apart conjunctions and existentials and things, it can also be used to split apart data. So here, cases is splitting A into its x, y, and z coordinates. And like we saw in the previous lecture, you can also use obtain instead of cases and get some names for these two. And we're using dsimp here just to clean up the mess that appears when you do cases. And so now we have this equality. Instead of saying A equals B, we are saying this structure built out of AX, BX, AX, AXY, AX, AY, and AZ is equal to the ones for B, and we can just rewrite and it closes the goal. This is such a common thing to need to want that you would rarely write that yourself. In fact, there's this X attribute you can stick on a structure, and it generates this lemma for you. And so if we'll try and prove the same thing again, we can now just use the X tactic, and it will automatically create 3 sub-goals, one for each of the X, Y, and Z. And then we can close all of them with this assumption tactic that just picks one of HX, XY, HY, and HZ to close the goal. And what the X tactic is doing is it's finding this lemma. It looks for lemmas that are tagged with X, and the X attribute on a structure generates a lemma that itself has the X attribute. So you either put the X attribute directly in the structure, or if you need a custom X lemma, which you could just search through Mathlib for, or maybe, for instance, the one that says functions are equal if their evaluations are equal, or sets are equal if their elements are equal, X will just search for everything that's tagged with that attribute. And generally, you can make a lot of progress on a problem by doing X and then doing dsimp. And so here we're showing that addition on points is commutative by doing X to split it into 3 goals, one for X, Y, and Z. We then use this semicolon and angle brackets, which says run the next tactic on all the goals. So we dsimp, which then puts all the goals in a nice form, which is just A.x plus A.x plus B.x equals B.x plus A.x. And then for all those 4 goals, we apply the global adcom lemma that closes the goal. Yeah.
So this X, the point is that it is kind of doing this recursively and not just.
Yes, exactly. So X works. This isn't an example of that, but X absolutely does work recursively, and you can be quite clever about how you make it recurse. So, like the simple example would be if you have a product type, and the second element of your product type is itself a product type. Then when you do X, you'll get 3 goals rather than 2, because it will recursively. It'll first apply X to get the first part, which is by itself, and the second part, which is the product. And then it will do X again on this piece and give you 3 goals. Yeah, I think you can do X colon 1 or something. And yeah. There is some way of combining the word X with a digit with some punctuation, and it will let you specify exactly how deep you want to go. You can also use show term before the X to see which X lemma it found, and maybe just apply that directly.
So, but if I know in that structure, do I have to write an X?
Normally, you would just stick this on it. So that will generate the lemma we wrote in the previous slide. And the lemma we wrote in the previous slide, we also tagged with X. So X has 2 different meanings as an attribute. When you put it on a lemma, it means run this when you run the X tactic. When you put it on a structure, it means generate a lemma with the X attribute. And then that lemma will be run when you use the X tactic. So on this lemma on the screen now is exactly what is being generated by the @X on this slide. Does that answer your question?
I wonder what will be generated for a general base structure.
It'll take all the fields and it will generate a lemma that says if you've proven each field is pairwise equal, then the whole structure is equal. If there are proofs within the structure, it'll throw them away because all proofs are always equal. If your structures are dependently typed, then instead of generating equals, it will use HEQ, which is heterogeneous equality, and normally things are started to go wrong if you have too many of those in your goal. But you can certainly play around with that. The other way to answer your question is write a structure that you think is crazy, stick X on it, and then print out the X lemma it generated and have a look at it. Yeah.
Same system also work for other attributes like that?
So there is a similar thing, simps with an S, and if you put simp with an S on a definition, then it will generate a handful of lemmas for you that are tagged with simp. But in general, it's up to each attribute to decide what it does when you put it on something unusual. Yeah.
Maybe to add that there's also like mathematical structures where the extensionality axiom wouldn't be something as trivial as this, but sometimes there's an easier way to prove the equality of stuff.
Yeah. So a good example.
Maybe some of the stuff is.
So a good example would be if you have the type of equivalences, so a function and an inverse that are like a 2-sided inverse. If you use this, the X lemma generator will be if the forward function agrees and the inverse function agrees, then the 2 are equal. but you know that you only need to check that the forward functions are equal. So you would write your own X lemma and tag it with X instead of using the built-in one. And the way you would do that is by essentially doing this type of thing, but discharging the other side goal yourself. So you do need cases to implement that type of thing. I guess since this has become a slide about the depths of X, the other thing that's maybe interesting is, what's a good example? For instance, there is an X lemma for linear maps from the tensor product that says to show that two linear maps from tensor products agree, it suffices to consider only pure tensors. And like all sorts of objects constructed in ways like that with a generator, there'll be an X lemma that says you only need to show they're equal on the generator. That is not in any of these slides or the exercises. Okay, so we did this, we did that. Let's finally actually add some proof fields to our structures, which is one of the things that makes structures very useful in Lean. So this is the type of points on the open disk with a certain radius. So the radius here is a parameter. We've got an X and Y field, and then we have this proof field that says X and Y is within the disk. So the sum of the squares is less than R squared. If we want to create a term of this type, again, we can use the light bulb trick to have it fill out the fields for us. We'll have an X field, a Y field, and a memdisk field. And this memdisk field is a proof, so we want to start it with the word by. And in fact, if you do the light bulb trick, it'll stick an underscore there, and then that underscore will itself have a light bulb, and if you click that light bulb, it will generate the word by for you. And so here, the goal is just some trivial statement about digits, so norm can fix it. Let's imagine now, instead of like creating an object of type open disk, we want to show something about open disks. So here I have P, which is an element of the open disk with radius 1, and I want to show it's impossible for the X coordinate of that element to be 2. So I intro HX, which gives me this term saying that it is equal to 2, and we're now trying to prove false. And because we have this P object in scope, we can do P.memdisk, and that gives us the property that was inside the structure, just like we would for P.x. And so now we have a statement that about P.x and P.y, and n-linearith is like linearith, but it can do inequalities, especially with squares in. So it essentially just calls linearith and builds up a context saying, well, everything that's square is positive is non-negative. And so that closes the goal. But the key thing is that the proofs are exactly the same as all the other fields. Some more examples of structures that contains proofs. You could have the structure of even natural numbers, which contains a natural number n and a proof that it's even. You could have a Pythagorean triple, which contains the 3 side lengths and the proof that the sums of the squares is as you'd expect. And you might have a structure that takes a function as a parameter. So this is the type of roots of f, where it contains the root x and a proof that f evaluated at that x is 0. And the exercises will have you produce in terms of these types. You can also have structures that are pure propositions. So you've already seen one, which is the AND structure. But here I've got this is-fizz-buzz structure, which might be familiar to people who have done silly programming practice interview questions, where you have to decide if something is a multiple of 3 or a multiple of 5. And so this is a proposition that has 2 separate fields, one for 3 divides and one for 5 divides. And in the exercises, there's an exercise that has you prove this is exactly the same as just an AND. So I've showed you how to define your own structures. Lean already has a pile of built-in structures, and sometimes you don't. Yeah.
Yes. Why don't we start adding the parameters to the structure?
So the parameters are things that appear after the name and before the colon, exactly like in a regular function.
Okay. Are they stored inside the structure?
No, they're part of the type itself. So for instance, an example would be a list. Well, a list isn't a structure, but like a list of n, the n is part of the type itself, the fact that the list is of natural numbers. It's not stored in the object. In like C++ or something, if you had an std array, then those parameters are the things that appear inside the angle brackets. Does that help? Okay.
But I'm confused by what you wrote. You said this colon prop, what does it mean?
Sorry, yes, this colon prop is telling Lean, so normally you can actually write colon prop or colon type on any structure, and by default, Lean will just work it out for you. But it doesn't work it out for you for propositions, and in particular, if you didn't write colon prop here, then is-fizz-buzz would be a type, which is mostly okay until you want to show that is-fizz-buzz n if and only if 3 divides n and 5 divides n, and then Lean will give you an error saying if doesn't work with types, it only works with props. So this is telling Lean, don't consider this a type, consider it a proposition so that it fits in the smaller universe, and you can use it in more places. I think there's a few sentences about this in the exercises, but not many more. Does that answer your question?
Yes, now I'm wondering whether I can also put something else than prop or type.
You can only put prop, type, or sort there.
Like type.
Or maybe things that expand to prop, type, or sort, yeah. Feel free to try and find weird things you can put there.
Yeah, but not N or R.
Yeah, that will not work. So Lean has some built-in structures. The product type is like one of the simplest structures. This again takes two parameters, the type for the left-hand side of the product and the type for the right-hand side. There's the subtype, which is there's this implicit argument, which is the underlying type, and then the explicit one is a predicate on that type. And you'd rarely actually write this out using the word subtype. You'd write it out using this curly bracket notation. And so this says I'm taking an x, an element of alpha, that satisfies P of x. And with these two pieces, we could have built the types we had in our previous slides. So for instance, we could have implemented the point as just this iterated product. And we could have implemented the open disk 2D as the subtype of pairs of real numbers such that this element square in the right way. But the downside of doing this is that for this point example, if we use that new definition, we have to write p.2.1 instead of p.z to get the third element. And that's not really as pleasant. So in general, if there aren't many projections and you don't care what they're called, it's fine to nest the built-in structures. But as soon as you want to give nice names for things, it's better to build your own structure.
Can I ask another speech?
Yes.
There's a colon type. Could this be inferred automatically?
Yes, this will be inferred automatically, but generally, the danger of not writing what types your defs are is that they end up being something you didn't expect them to be. So if you think you know what type something's going to be, it's often a good idea to write it in case you're wrong, and then you can work out why you're wrong immediately rather than later when things go. Yeah. And in the exercises, it has you show that these types are equivalent, as in there is an equivalence between the first type and the second. Then there's a map in both directions. Okay, let's move on to, oh, sorry. So p.z was for our original point, where we just had a z field.
Right, and that's a third field, right?
That's the third field, yeah. No, okay, so there's a p and there's a p prime in this sentence.
Yeah.
The p is the one from many slides earlier, which was defined. Yeah, so it's literally just pulling out this. Can I remember where I was? Can you tell my mouse is on a slope? Oh, where was it? Yeah, it was this one. The p prime is referring to this type. And so .2 is this piece. And then .1, oh, that should be .2. Is that what you were saying?
No, yeah, okay.
Yeah, that should be a 2.
But then if there are 4 fields, it would be p.2.2.2 or something.
Well, so to be clear, there aren't 4 fields. It's 2 fields nested inside each other multiple times. So
the point was like WXYZ.
Yeah, if the point was WXYZ and you wrote it in this product style instead of listing 4 fields, then yes, it would be 2, 2, 2, 2. Yeah, and so it doesn't really scale very well. For the p.z, you could have written p.3. That would have been fine. Because when you have a structure that is just a flat structure with a list of fields, you can number them from 1 to whatever.
Okay, so I was about to ask, and I think you probably answered. I was about to ask why it's called 2 and not SMD.
Yes, exactly. It can be either. There's special notation. You could write, for product, the convention is usually just to write 1 and 2. For other types, it kind of depends, and there's no real convention in Wild West. Yeah. Okay. That has done something weird because I jumped slides. Okay. Right. Now I'm going to look at algebraic structures. So earlier, we proved that addition on points was commutative. And like Lean also knows that addition on, oh, this unfortunately seems to be Lean 3 code I've written here. Sorry about that. We've proved that Lean knows that rational numbers have commutative addition and that real numbers have commutative addition. And you really don't want to write this lemma over and over again, because then any lemmas that use it have to be written over and over again, and the library doesn't scale at all. And so what you need, of course, is, sorry, wrong order. We've seen type classes for notation. We had this add class that lets us use plus notation. What we need here is a type class that lets us say addition is commutative. So that so we don't have to repeat everything. And so the obvious type class here is saying that A is an additive commutative group, which gives us addition and it gives us the fact it's commutative. And so what we do is we write in square brackets the type class that we want, the type we want it to apply to, close the square brackets, and then what will happen is if we try and use this lemma with a certain lowercase a and b, it will look at the types of a and b, find a, and then it will look for an additive commutative group and have it to prove this lemma. And so here, this adcom group.adcom is referring to a field of this hypothetical adcom group. And so what you would do is after you've defined this adcom group class, you would show that points are an additive commutative group, you would show that the rationals are an additive commutative group, and the same for the reals, and then you can prove all three lemmas the same way. This obviously isn't just a lean trick. This is algebraic structures as done in mathematics. And so this is just a list of structures taken from mathematics and lean. So you've got a partially ordered set defined from a set in a binary relation. We've got a group. We've got a bunch more things down the bottom. So things going as far as metric spaces, and there was a topological space exercise that didn't fit in the slide. And just looking at the top two, we can pretty much directly translate these sentences into lean. So like each bit is describing one field of the structure. The only slightly interesting bit here is when we say a set P, we've put that as a parameter of the structure, and everything else we've put as fields. And this is just convention for how things are done in lean. In Coq, things are actually done differently, and it's put inside, but that is because Coq doesn't use type classes, they use a different system. For type classes, because usually you know the set P already. So for instance, you're working on the natural numbers, you want to use less than and lemmas about inequalities in natural numbers. Lean says, okay, I want to go find some results about the natural numbers, so it needs that P to be an argument to the class such that it has something to look it up by. And what I've written here for the group isn't actually how Mathlib writes it. It does have these associative left identity, right inverse things, but that just makes things less pleasant for new users. So what Mathlib actually contains is it just writes these things out in full. So here you've got associativity. We're referring to this mole field that we defined earlier. This is still pretty unpleasant because you don't want to write mole using mole. We had this notation earlier, and now we seem to have lost it again. So what we can do is instead of having these three fields, mole, one, and inth, I have forgotten the order of my slides. Once we've defined this, we've got two problems here. It's messy inside, so it's full of moles, ones, and inths, which are hard to read. But also, anyone using this group still can't get the notation. So we need to tell lean how to turn an instance of a group into an instance of add of mole, one, and inth. And so here we're saying we have an instance called group2mole that takes in some group instance and produces some mole instance. And what this means is that if lean is looking for a mole G, it'll find this instance and it will say, oh, I found an instance, but in order to apply this instance, I now need to find a group G, and it will continue its type class search for the bigger class. And it will keep going until either it hits the end of its search or it finds a solution. But like this is a lot of boilerplate. We don't want to write this. So instead, we can put the 2 mole, 2 1, 2 inth fields directly inside the group. And this means we get the nice notation. We still have to tell lean that these exist as instances. So this attribute instance is saying, the group2mole that you defined automatically for me, please tag it with the instance tag that we tagged it manually with earlier. And this is still kind of messy. We can do even better. There's this, There's this extends keyword that lets you say, here are a bunch of existing type classes that I would like my type class to extend. And what that means is that the notation and lemmas are available inside the definition of that type class. And it also generates these lemmas, these instances that say every group provides a multiplication, every group provides a 1, etc. Mathlib has a somewhat strange definition of a group. Like often when you see a group introduced mathematically, they'll say a group has some operator and then they'll pick a symbol of their choosing. Lean has decided that the canonical operator for groups is the asterisk, and if your operation is plus, tough luck, that's not called a group, that's called an add group. And if your operator is called something else, tough luck, you better make it look like add or multiply. So for your exercises, there is essentially just rewrite this in the additive way. It does sound like it means you would have to write everything in the library twice. There is this toAdditive attribute in Mathlib that generates some stuff for you, but I'm afraid the exercises don't show you how to use it. If you search for toAdditive on the Mathlib docs, hopefully you can find something useful if you're curious about this. Yeah, exercise, write the additive version.
So this means if I define some new kind of I don't know, group-likely thing with a star, and I put x to additive in front of it, then automatically.
No, you'll unfortunately get. Sorry, when you say star, do you mean this asterisk, or do you mean? Oh yeah, yes. You can't define it on the. You can't put it on the on the class. But if you define a lemma about groups, so I don't know, you show that in commutative groups, A times B times C is equal to C times B times A. You can then put two additive on that lemma, and it will generate the lemma that says the same thing, but for addition instead. And you can do the same for definitions, like you might define the triple product as A times B times C, and it will then define the triple addition as A plus B plus C. I think there's some quite good documentation on two additive that gives some examples like that. So we've now seen how groups are defined. How do we show something as a group? Often you would first define what its operations are. So here we're going to look at the permutation group over a type alpha. The one is just the identity equivalence. Multiplication is composition of the functions. And the inverse of an equivalence is just the inverse function inside it, which Lean has defined all these things for us already. And now that you've defined this one Marlin inv instance, when you get to saying instance group, Lean will automatically find these one Marlin inv instances you already defined. So all you'll have to do is prove these things are associative and do the right thing with one and inverse. And this isn't in the exercises because it's boring. The exercises just show you how it's done. Another maybe more interesting example is how you can chain type classes. So we, yeah.
Just to show that I understand. So when you say, so, okay, if I define the notion of group myself, then I could either create a field which I call one.
Yep.
Or alternatively, I just say it's an instance of one, and it has a field called one.
So
which moreover can be written as one. Is this?
So when you say define a group yourself, you mean a thing that is a group, or you mean your own type class called group?
Sorry, I want to define a class or group myself.
You want, okay. So yeah, your choices were you can directly put the mul1 and in fields in like this, and then you have to do all this manual work, and you don't get any nice notation in here. Or, I guess this is like an intermediate step, but the other choice you would make is you put them after this extends keyword, and that generates all of the boilerplate for you. If you wanted to define your own group that used a different symbol that wasn't add and it wasn't multiply, it was like an asterisk, it was like a diamond or something, then you would probably write something that looks more like this. Yeah. Or you would build your own diamond, diamond1, diamond inv, whatever classes. Two operations is enough for anyone. Okay, so chaining type classes. We saw the example earlier of if you are looking for a one, you can tell Lean that if it can find a group, then it solved the one. Here you can do things, you can say that a product of two groups is a group, or a product of two things with one has a one. So the one of the product of two things is just the pair where the first thing is a one and the second thing is a one. The product of two pairs is the product of the first, product of the second, etc. And each of these is saying, if alpha has a one and beta has a one, then the product type also has a one. And then you can do the same thing for a group. So you can say if alpha is a group and beta is a group, then the product is also a group. And I believe this one is in the exercises. And the trick here is to use the X tactic, which will split it into two pieces and let you equate the first half and equate the second half. And you, or maybe, no, so the exercises have you do this for points. So for a general point over an arbitrary ring, if you know, over an arbitrary additive group, if you have a point over an additive group, then the points themselves are an additive group. Or more realistically, if you have a point over a ring, then the points themselves are an additive group. Okay. This is pretty much the end of this talk. There's just two slightly more interesting and confusing things that type classes are used for. One of these things that's interesting is that if you actually try to use Lean's Matlab's built-in group, which is what you'll want to use outside of this exercise session, and you use the light bulb to generate all the fields for you, you'll see you get this massive pile of fields that looks way longer than the group I just showed you. And in particular, the ones that are in bold are the new ones that kind of seem nonsensical. So n power is powers by natural numbers, z power is powers by integers, and division is just division. And all of these, you can argue they're pointless because you can build them trivially from the other fields. And there are silly technical reasons why these are here. There's this paper by Anna Bannon that explains it a little bit, and there's some citations that explain it some more. But the simple thing to realize is that you can often just delete these auto-generated fields, and Lean will fill them in with a sensible default. So if you delete the in field, it will fill it in with x times y inverse. Sorry, I said that wrong. If you delete the div field, it will fill div xy in as x times y inverse, and it will fill in all the extra proofs for you too. So if you see fields you don't understand that you think are mathematically meaningless, try deleting them. Lean will probably let you get away with it. Yeah.
So in the previous slide, you were saying you were defining a group, say by saying instance of one of Muller int and so on.
Yeah.
Could you also directly say I define a group and then I define one more?
Yeah. So I could have taken this line and the other one, and I could have put them in here and never done this first step. It gives exactly the same thing. The reason you might want to do this first step is that if you define this one Muller inf, you can then write the lemmas saying the first part of 1 is 1, the second part of 1 is 1 for all these operations. And then when you get to proving these things, Lean already knows all those lemmas. Whereas if you put it all in one place, you don't have any space to tell Lean, here are some lemmas about how I've defined one Muller inf before you have to start proving things, which may or may not matter. Ultimately, yeah, you can put them all in one place. You can do them separately. After you've done it, no one else will care. It's only while you're getting to the point of getting the group structure that it matters. I guess there's a slight asterisk here that by building things up like this, if you have a type that isn't a group but does still have a 1, this gives you the 1, which maybe someone cares about, maybe they don't. If you have the hierarchy that you're going to see in the next lecture, that's a good reason for building things up piecewise, because someone might need an intermediate piece. Okay, where do we get to? We did this one. Last slide, we said that instances were for things that are canonical, but sometimes you have a non-canonical instance. So maybe you want a type where the multiplication is reversed. So let's think of an example, maybe permutations. You want permutations, but you want multiplication to mean reverse composition instead of regular composition. And so what you would do here, or at least one way of doing it, is you define a structure with one field, and then instead of having an instance on the original type that is non-canonical, you have the instance on this new type, and on the new type it is canonical because the name of the new type is telling you it has this different instance. So here you say multiplication on the opposite type is defined on x and y as the opposite of the reverse multiplication. And this is the thing I said I'd tell you at the beginning of the talk. You can, instead of having the constructor be called mk, you can name it whatever you like by writing the name you want and 2 colons after the where clause. So what this is defined is a structure called null opposite, where the constructor is called op, and there's a single field called unop. And so here, we're taking in an x and a y, which are of type null opposite. We're accessing the unop field on y, we're accessing the unop field on x, we're multiplying them in reverse order, and then we're using the constructor, which is now called op and not make, to put them back together as the reverse multiplication. And then you prove that the opposite of the product is the product of the opposites, and the unopposite of the product is the product of the unopposites. And now you're ready to show that this forms a group if alpha is a group. Some other examples that I won't go into in detail. That different has 3 Fs. You can put different norms in a vector space. So you might want the L2 norm or maybe the L infinity norm, and like all of those are in some sense canonical, none of them are in some sense canonical, so maybe you just don't pick anything. And when you want to use one specifically, you work with LP on that space instead, and then you can specify exactly which P you want. Instead of reversing multiplication, you might want to reverse the order of comparison. So you might want to say that 2 is less than 1 instead of 2 is greater than 1. And you might want to translate something about addition into something about multiplication, not via 2 additive, but by casting it into this multiplicative type. So an example would be if you have a function that converts addition into multiplication, so for instance, exponentiation, you could just define that as a monoid morphism from multiplicative A to B, or multiplicative R to R, right? Because it's converting the addition in the domain to multiplication, and now you have multiplication on both sides, and you can use things in Lean that expect multiplication on both sides. Okay, this loosely follows section 6 of Mathematics in Lean. I've written some exercises that are pretty much based on the content of these slides. Everything in the exercises is code from the slides. If you get fed up with those, or you finish those, then do the Mathematics in Lean ones, especially the last one, which has you build up this Gaussian integers class structure. What I will briefly show you is that I can't exit this window. I was hoping that would still be open. Any questions while that loads? Yeah.
So we define a product type for, and you also define the subtypes. Is there also a possibility you define like addition types?
So addition types you can define, but they're not structures. They are inductive types. So there is I think the type you're thinking of is the sum type.
Yes.
Yeah, so that exists in Lean, but because it has two constructors and not one, it is not considered a structure. Structures are things that have exactly one constructor. But you can absolutely build any type you like out of those two. It's just not in scope of this talk. I think theorem proving in Lean probably has some explanation of that too. Yeah.
So this means if say I want to build my own math thing or something like this.
Yeah.
So I probably start define structure for monoid, and then I define a group as a class which extends monoid, and then
that is in the next lecture. Yeah, you're correct, but I was trying not to tread on Mark's toes too much. Yeah, so in here there is structures and classes. There's this S00. And the trick I want to show you once this loads, I think I've committed the crime of opening a Lean file while the cache is being got. I should have opened this earlier. Any further questions while this is loading?
How did you make your slide?
I used reveal.js, and I wrote far too much awful HTML that I never want to have to write again. I wouldn't necessarily recommend it. But you can view source on the slide link that was on, it's in the examples, and what you see is exactly what I wrote. This isn't looking like it's going to load, so what I'll just tell you what to look for. There's this outline bottom in the bottom left corner. If you expand that, it'll show you where the exercises are, so you can click in this outline to jump to the exercises. But this isn't loading on this PC, so whatever. Oh. Yeah, so like you can see the things in the slides and the things in the exercises, and you can think, oh, I want to go to an exercise about functions and operators, and if you click that, it's asking you to define the dot product with 2 points.
So that's what you do with this section?
The section, yeah, sections will appear in this outline sidebar. They also appear up here. That's not, section isn't used that much in that way in MATLAB because it didn't used to do this in Lean 3. This is a new feature of VS Code for Lean 4. Cool. That is all I have. Good luck with the exercises. Is that a question? No, it's a hands.